Hello, I'm David Lee with the Virginia Asphalt Association, and this is Chapter 2, Components of Asphalt Concrete Mixtures as part of the Asphalt Plant Level 1 class. For our learning objectives for this class, we're going to talk about the understanding of what materials are used to produce an asphalt concrete mixture. We're going to talk about what physical attributes of those asphalt concrete mixtures pertain to each and every one of those products. We're going to talk about what types of asphalt mixes and binders are used in Virginia, specifically for mainly VDOT, the basic aggregate and asphalt properties, and we're going to become familiar with the common asphalt concrete volumetric terms. So, let's first talk about what materials are used in asphalt concrete mixes. And let's specifically here talk about the asphalt cement or the binder. That binder, as you can see in the picture you have there, is basically the glue that's used, and it's about 4 to 6% of the total weight of that mixture. And conversely, if you think about it in terms of volume, it's about 10 to 14% of the total volume. And if you think about volume, volume includes the air that's in that particular mixture sample, so therefore it's going to be a higher number in this case. And as I said, it's the glue for the mixture. So it binds those aggregate particles together. It's basically gluing all those particles together to form an asphalt concrete mixture. And it provides cracking and rutting resistance. So when you have traffic on that roadway, you need to make sure that it's stiff enough to be able to produce a mixture that'll handle the loads that are included in that. So you don't want it to crack over time, and you don't want it to rut. So you got to have that resistance to those products. We're also going to talk about the total percentage that may include RAP and RAS. RAP is asphalt, is a recycled asphalt pavement. RAS is a recycled asphalt shingles. We don't use a lot of RAS in Virginia, but we do use a whole lot of RAP. In fact, I would say 99% of the mixes in Virginia use some percentage of RAP. And that RAP contains an aged binder in it, and it's included in our mixtures. So we also had just talked about the aggregates. So the aggregates that are part of that mixture, they're about 94 to 96% of the total mixture by weight. And again, when you look at that weight-volume relationship, if you think about it, we just talked about it has the binder in it and it has air in it as well. Well, the aggregate becomes 75 to 85% of the total volume. So if you think about it again, 94 to 96 of it by weight, because it's just mainly the aggregate and the binder by weight. And then if the volume is the liquid asphalt, the air, and the aggregates are about 75 to 85% of the total volume. So there's fine aggregate and coarse aggregate in our mixes. The fine aggregate is the material that's smaller than the number 4 sieve. So it's all the material that passes through a number 4 sieve. The coarse aggregate is all that material that's larger than a number 4 sieve. So it actually is retained or above the number 4 sieve. And again, we always have to remember that our mixes contain both RAP and RAS, and there are aggregates in those products, and those aggregates are included in the aggregate as part of that mixture. So let's go back to the binder that we were talking about earlier. The binder has to have a number of properties. These include the consistency of that binder, the purity of the binder, the durability. You have cohesion and adhesion that need to be included. And temperature susceptibility is critical for our binders. And that relates to the aging and the hardening aspects of our asphalt cements. Okay, let's talk about the consistency of the binder. That consistency is the degree of fluidity or plasticity of a binder at a particular temperature. So they have a specific property at a given temperature. So the consistency of those binders is going to vary obviously with those temperatures. So when a liquid asphalt is colder, it is obviously harder. When a liquid asphalt is hot, it tends to be more fluid. And those binders are graded based off of those temperatures. So the consistency is at a specific standard temperature. Purity of the liquid asphalt is critical. You'll find that there are a degree of purity, and there are typically some types of additives that can be used. Some states allow some of these additives to impact the grading of a specific asphalt. Those could be polyphosphoric acid or refined engine oil bottoms. Those can be added to change the properties of a liquid asphalt, but those can also be considered a contaminant. So many states do not allow the use of these types of additives. Let's talk about durability now. So durability is the measure of how asphalt binder physical properties change with age. It's also known as hardening. So as a liquid asphalt gets older, it gets harder. So when that binder ages, becomes stiffer or more brittle. Qualities that complement the binder's durability are its resistance to swelling, stripping is very critical, oxidation also impacts that hardening we talked about, and then obviously the wear of the mix itself. All right, so let's talk about adhesion and cohesion. So first, let's talk about adhesion. Adhesion is the binder's ability to stick to the aggregate in the paving mixture. So we want those particles to adhere to one another, to create a mass that can handle the loads of the traffic. Cohesion is the binder's ability to hold the aggregate particles in place in the finished pavement. So obviously when loads are going around, it wants to move, so it needs to be cohesive and stay together. Together, these properties determine how well a road will hold up to traffic, weather, and all the other forces that they encounter. Let's talk about temperature, susceptibility, and viscosity. Temperature susceptibility is the effect of temperature on the binder. So binders are thermoplastic, if you think about it. So as the temperature of the binder decreases, it's going to become harder. We talked about that earlier. As the temperature increases, it's going to become softer or less viscous. So if you look at the chart that's on this slide, you'll see that as the temperature increases, all the way up to this slide, it's 275 degrees, it is less viscous or softer. As the temperature decreases, in this case all the way down to 0 degrees Fahrenheit, it's obviously more viscous or harder. So let's talk about aging and hardening of those binders. Binders harden in the mixture during construction and over time. So over time, as we've talked about, they're going to get harder. But most hardening actually occurs during the mixing process at the plant itself. When you think about it, and you're producing an asphalt concrete mixture, that mixture and the aggregates are going into the drum at 400 plus degrees. And so when you insert the liquid asphalt, it's actually sprayed into that drum. It's sprayed in at that highest temperature. So if you think about it, you're never going to see that temperature again. At 400 degrees, you're seeing a very high temperature. So a lot of hardening occurs. In fact, most of the hardening of your liquid asphalts occur in the plant production process. And that's caused primarily by oxidation over time beyond that initial production, which occurs most readily at higher temperatures and when you have thin binder film. So again, when we were going through the plant and we were spraying it in there, that binder film is much thinner than it is in the finished product, so you're going to get a greater level of hardening. So now let's talk about the SUPERPAVE PG binder system. VDOT uses the Massacre system, MSCR. So those are based on certain degrees of PG binder grading. PG stands for performance grading. And those can be like a 64S minus 22. Those are for lower traffic levels and truckloads in what we call our A mixes. We have a PG 64H minus 22 for the moderate levels. Those would be our D mixes. And you can also get a 64H by using a 64S minus 22 and inserting that wrap we spoke of earlier. So if you include wrap, that wrap has a hardened binder in it already. You combine that to achieve the 64H minus 22 properties. And then lastly, we have a 64E minus 22. Those are for extremely high levels, such as interstates. And in Virginia, those require polymer modification. Binder testing is performed by the liquid supplier, so all that has to come to the plant already tested. So it already is determined that it meets these properties. All binders that are provided have to go through the VDOT certified source program. So what they do is VDOT goes through and determines that those sources are verified and that they can produce a high quality mix in accordance with all of their specifications. And each binder grade must be approved by VDOT. So not only is the facility approved, but each binder has to be approved by VDOT. As I talked about earlier, the aggregates again, we'll just repeat this, are 94 to 96% of the total weight, and they're 75 to 85% of the total volume. And don't forget that wrap that I talked about, the recycled asphalt pavement, can be part of that aggregate fraction in your mixes. And primary responsibility is to carry the load. So when you're think about it and you actually have the traffic on an asphalt pavement, that traffic has to be carrying a load. So the aggregates are what carries the load, and then the binder holds it all together. There's all kinds of sources for aggregates. Most of what comes in Virginia come from industrial prepared sources, but there are also naturally occurring sources, particularly when we talk about sands. So on the naturally occurring side of it, they're basically a pit. So they go out there and they actually remove the material from this pit, and it's either a sand or it's a gravel. So it is what it is. All they have to do is screen it, and it's sized properly, and they're done. Then there's the industrial prepared. In most cases, that's what we have in Virginia, and they actually take rocks and they go through a crushing process. So they physically go through a process to produce those aggregates, and then they're screened to a particular size. There's also synthetic aggregates or artificial aggregates. In Virginia, those are mostly things such as slag. So there are a few sources of slag that are from the steel making process, and that slag can be also processed to produce aggregates. So it's an industrial prepared product as well. Let's talk about the aggregate characteristics. So we have a number of characteristics that these aggregates have to meet. They have to meet a sizing, a grading, obviously. They have to be clean, tough. They have to have a soundness, which is more of a freeze-thaw function. They have to have a particular shape, so they have to be flat and elongated is a specification that determines whether or not they're too flat. Then there's surface texture. We want a rough surface texture on it to hold that aggregate together and also to hold the binder to the aggregate. There's an absorption. We want a little bit of absorption because we want that aggregate again to bond well to the binder, but we also don't want too much absorption. And then there's its affinity for the binder. Will the asphalt and the binder stick together? That's the affinity. Well, let's talk about size and grading. Size, the distribution of the aggregate is determined by a sieve analysis. And that sieve analysis will actually divide those into certain particle sizes. Those particle sizes determine the stability and ultimately the density of the mix. And if you look at this chart, you'll see that you have an aggregate size, and it's broken down into a number of different sizes. You have the coarse aggregate. Again, that's the larger aggregate fraction. On the left side, if you look to the far right side, as we spoke of earlier, that's the fine aggregate fraction. And then in the middle, the very finer material is either a filler or a mineral dust. And those are very fine materials. Let's talk about cleanliness. The cleaner the aggregate, the better opportunity for the binder to adhere to it. So if you think about it, if you have paint and you're painting a room, if that wall is dirty, the paint wants to stick to the dirt, not to the wall. Same thing with these aggregates. If the aggregate is dirty, the binder is not going to want to stick to that aggregate very well. Aggregates that contain foreign or deleterious substances are undesirable in our concrete mixtures. We don't want things such as clay lumps or organic material to be included in our mixes. And that's measured through something called the sand equivalency test. That's AASHTO T176. Toughness. Aggregates should resist crushing and abrasive wear during manufacturing, placing, and compacting of those mixtures. So they have to be relatively tough. We don't want them to break down easily during those processes. And that's measured through a test called the Los Angeles abrasion or the LA abrasion test. And it's basically a drum, and you put your aggregates in the drum, and then you put these steel balls inside that drum, and you turn it, and it just runs a certain number of revolutions. And those balls beat that around, and they determine just how much that aggregate is going to break down. So therefore, it determines the toughness of that aggregate. There's another test called soundness. Aggregates must be resistant to the breakdown or disintegration under action of wetting and drying. So if you think about it, our pavements are going to go through a series of climatic conditions. So they're going to get wet, they're going to get dry, they're going to get cold. And we want it to be resistant to freezing and thawing. So when that aggregate gets wet, we don't want it to break down when it freezes and thaws. And that's measured through a test called the soundness test, and that's AASHTO T104. Let's talk about particle shape. So we want those particles to have a certain shape. We measure that by determining the flat and elongated pieces of it. So you don't want to have particles that are way too flat, And certain particles can be both flat and long, and we certainly don't want those because that orients those particles such that they can lay flat and you don't get that interlock between the aggregates. We want our aggregates to be suitable for use in asphalt, should be more cubical rather than flat, just like I said. So we want them to be a cubical shape and not flat and elongated. Angular shape particles exhibit greater interlock and internal friction. So again, if you have particles that are rounded, then they tend to want to be like ball bearings and move around. But if they have a particle shape where they can interlock and they create their own internal friction. And that's measured through ASTM 4791 on a maximum to minimum ratio. Why is that important? As I just said, if you look on the image to the left, you see rounded particles, all the same size. If you think about trying to drive across something that's a lot of ball bearings, they're going to want to move around, and they move around very easily. And therefore, you can have rutting and your pavement will fail. If you look on the right side, those articles have a proper distribution in not only size, but also particle shape, and they can interlock so that that load, when it goes across it, those aggregates again are carrying the load of the pavement structure. So here's the shape. We're determining the ratios. If you look at this picture, you'll see various sizes of flat and elongated particles. On the far left, you'll see a 2-to-1, then there's a 3-to-1, a 4-to-1, and a 5-to-1. Our SUPERPAVE specifications require a 10% maximum measured on the 5-to-1 with a max to min dimension. So that 5-to-1 is the maximum to minimum dimension that we can have, and that cannot exceed 10%. Let's talk about surface texture for a second. We have coarse aggregate angularity, and we have fine aggregate angularity. And these influence the workability and strength of the asphalt concrete. We want a rough sandpaper-like texture so that we can have, again, that bonding that we talked about. And these are measured through ASTM D5821 for the coarse aggregate angularity and AASHTO T304 method A for the fine aggregate angularity. Now, some aggregates lose surface texture and polish under traffic, and we don't obviously want that in our surface mixes. Calcareous aggregates such as a limestone, those tend to polish, and over time they will polish such that the pavement becomes slick, and that's obviously detrimental to the safety of the traveling public, and we can't have that. Whereas siliceous aggregates such as a granite, they tend not to polish. So we require those types of aggregates in our surface mixes because they won't polish over time. So keep in mind that you've got it to get the proper skid resistance, you also have to have the proper aggregates in your mix. Now, absorption. The amount of water that's absorbed into aggregate. This is indicated by its porosity. The degree of porosity, a certain degree of porosity is desirable. Like I said earlier, you want a certain amount so that you can get a mechanical link between those particles. So when the binder is actually inserted into the mixture, you want a certain amount to absorb into that aggregate. That increases the bond, and therefore you get a stronger pavement. But you don't want too much. If you get too much absorption, then what happens is it increases basically the cost of the mixture because you lose that liquid asphalt into the aggregates, and it increases the quantity of aggregate that has to go into that mix to begin with. The affinity for the binder. This is the ability of the aggregate to be coated with binder and remain coated in the presence of water without stripping off. And our aggregates either hydrophobic or they're hydrophilic. And hydrophobic aggregate is more prone to stripping. And the need for anti-stripping chemicals or hydrated lime are obviously present. A hydrophilic aggregate is not prone to stripping. However, keep in mind that VDOT always requires an anti-stripping chemical or hydrated lime in all of their mixes. So whether you have a hydrophobic or a hydrophilic aggregate, VDOT, as an insurance policy, has a certain requirement that you meet this test. So you still have to use a chemical additive or hydrated lime in VDOT's mixes. VDOT also requires VTM 13, the Boyle test. And that just determines that anti-stripping factor for their mixes. So that'll help you determine whether or not you have an additive in the mix and whether or not your mixes are going to be stripping susceptible. Let's talk about aggregate storage. Aggregates must be handled, hauled, and stored in such a manner that they minimize lots of things: segregation, degradation, contamination. Then you have a stockpile on the ground. You need that stockpile to be on a hard surface, if at all possible. What many plants do is they actually will pave their lots so that they ensure that they're not getting those deleterious substances I talked about earlier, and therefore it's on a hard surface and you won't get any impact from that. You want a clean surface. So that surface, again, trying to avoid getting those clay lumps or deleterious materials that come from the yard, they don't get mixed into your stockpiles. And you want it well drained. So again, if you have a hard, clean surface, you want it well drained because you don't want those aggregates to get too much water. So when it rains a lot, those aggregates are going to get wet. If it drains well, those aggregates will dry more rapidly. And you can have mixtures that, when they go through the plant, they don't require nearly as much time to dry that aggregate. So when you're producing an asphalt concrete mixture, the aggregate's inserted into the drum at a certain temperature, and you want to get those aggregates dry. Well, obviously, if they're extremely wet, that takes longer and more fuel to get those aggregates dry. So let's talk about now the physical characteristics of asphalt concrete mixes. We're going to talk about the stability, the durability. We're going to talk about permeability and workability, as well as flexibility, skid resistance, stripping, and void content. So stability. Stability is the ability of the asphalt mix to resist deforming and rutting due to traffic. You can see right here in this picture, this is one that obviously rutted. So for whatever reason, it did not remain stable over its life and it rutted. And this is what we're trying to avoid with our mixes. So we need stable mixes. We need durable mixes. Durability refers to the asphalt mix's ability to resist cracking, to resist stripping, and rutting due to traffic, weather, and the environment. And one of the most important factors we have is permeability. For dense graded mixes, the resistance of air and water to pass through the mix is called permeability. What you see here is a field permeameter, and basically what you do is a very simple test. You pour water into the permeameter and you see how fast that water flows through your pavement structure. You want pavements that have low or almost zero permeability. You don't want that moisture to get into the pavements. Obviously, when it does, you increase the chances for freeze-thaw failures, as well as just the load and the water flowing through that mixture can cause stripping. So workability. Workability is the ease in which a mix can be moved, placed, or compacted. So you can see here a gentleman that's over there trying to work a tie-in into a driveway. Some mixes are more workable than others. So a field crew, they obviously like very workable mixes. It'll produce a better product. You can do handwork where you're tying into a driveway or you're tying into an intersection. You can get a nice, smooth, and easy joint with a workable mix. When they're not, then it can create all kinds of difficulties in trying to get those. Flexibility. Flexibility is the ability to adjust gradual settlements and movement in the subgrade. So again, asphalt pavement is a flexible pavement structure, whereas something like a concrete or a hydraulic cement concrete, it's much more rigid. One of the benefits of asphalt pavements is they do remain flexible, and they can handle typically gradual and small movements and settlements in the subgrade. And you need fatigue resistance. That fatigue resistance is the ability to minimize cracking from traffic or the environment. So over time, you're going to get more and more traffic going across that roadway, and you want that pavement to resist that fatigue that's caused by, in this case you see in the picture, a tractor trailer going across it. It needs to be strong enough such that that fatigue doesn't cause the cracking that you see on the right. And I talked about earlier the polishing characteristics of our aggregates. We need a pavement that has good skid resistance. And that provides adequate friction, particularly during wet conditions. So as you obviously know, when you're traveling on a roadway and it's wet, it's going to typically be a little bit more slick, and we need our pavements to have a lot of skid resistance. The more skid resistance we have, the safer it will be for the traveling public. Now let's talk about some of the mix types. In Virginia, we have dense graded asphalt mixes. We have what we call a stone matrix asphalt, or SMA, that's used on our high-end roads like our interstates. And then we also have open graded asphalt mixtures. So let's talk about our dense graded mixes first. For our surface mixes, they are most commonly used in Virginia. We have SM475, an SM9.0, an SM95, and an SM12.5. Those are all of our surface mixes. Then we have what's called an intermediate mix. That's the mix that's typically placed on the layer right below the surface. And that's always an IM 19.0. And then lastly, right above our sub-base aggregate, we have our base mixes, and those are BM 25.0. And you look at the nomenclature, you'll see that those last numerical digits, in reality, those are all in metric, because BM 25, we'll start down at the bottom, BM 25, that 25 is 25 millimeters. That's essentially 1 inch. And IM 19, that's 19 millimeters, and that itself is about 3/4 of an inch. And I won't go through all of them, but on your surface mixes, SM 12.5 would be about a 1/2 inch, and SM 9.5 would be about 3/8 of an inch. Like I said a minute ago, stone matrix asphalt, that's our premium mix. That's the mix that we use on our interstate highways and our premier primary roads in Virginia. So that's the one that we use where we really need the most longevity we can possibly get. So commonly it's used on, again, on the interstates. We use it on high volume primaries. On the surface mix side, we have SMA 9.5 and SMA 12.5. And again, that's the same metric equivalent. So 12.5 is that top size 1/2 inch, 9.5 is the 3/8. We have an SMA 19 as our intermediate mix, but we don't use SMA in our base mixes. We continue to use the BM 25 dense graded mixes that I spoke of on the last slide. So open graded mixes. Open graded mixes have been around really for a long time. They're becoming more and more prevalent. They consist typically of 1 or 2 aggregates. So again, you want, in this case, that water to flow through the mixture. So I talked about permeability earlier, where we were trying to create a pavement that it was very low in permeability. Well, in this case, we're doing the opposite. We're trying to create a mix that actually has a high permeability that will allow water to flow through it. You're going to have very little or almost no -200 material. So again, you don't want a lot of fines in there because you need that open void structure. 2 of the most common types, we have an open graded drainage layer. Those are placed down in your pavement so that any water that gets into the lower levels of your pavement structure, that can be carried away from that pavement structure. And then we have a porous asphalt mixture, a PAM. Again, we have PAM 9.5 and PAM 19.0. Those are typically used in constructing a pavement where you want the water to flow through it. We're seeing this more and more in certain parking lots where they're trying to get as little water to drain away from that parking lot as possible. They want it to drain through it into an aggregate base structure that actually carries the water away from that point. So let's talk a little bit about some physical characteristics. We're going to talk about voids in the total mix. Those are also sometimes called air voids. We talk about VMA, which is voids in the mineral aggregate, and we're going to talk about VFA. That's the voids filled with asphalt. And then along with these voids, we also want to talk about FA ratio because that also impacts your void structure. And that's the ratio of the number 200 material, i.e. those fines again that we talked about, to the effective asphalt binder content. And if you look in this chart below, you'll see where you actually have the air. Again, we spoke of really early on in the presentation. We have the binder, and then we have the aggregates down below it. So we have the VMA, which is that voids that are filled with air, and then we have also the voids filled with binder, the effective binder. That is the VMA, and then we have the voids in the aggregate or in the stone. So in summary, we have 2 primary components of asphalt mixes. They're called asphalt binder and the aggregate. And you can also get those from the RAP or from RAS. Again, RAP is recycled asphalt pavement, RAS is recycled asphalt shingles. Asphalt mixes must have several physical properties such as durability, stability, and skid resistance. And then there's 3 primary types of asphalt mixes that are used in Virginia. The dense graded side is your surface mix, SM, your intermediate mix, IM, and your base mix. And then we also have the premium SMA, the stone matrix asphalt. And then as I just spoke of, we have those open graded mixes. Remember that we have 3 primary binders that are types that are used in Virginia. For our A mixes, we typically use a 64S For our D mixes, we use a 64H, and our E mixes, those all have to be polymer modified. They're called a 64E. So again, awareness of these volumetric terms is helpful in understanding AC production and lab results. So at the end of this, you have some questions and some knowledge checks. If you'll go through that, you can check with your facilitator if necessary, or take time to go through each and every one of those to ensure that you understand these terms. Thank you.